Right now, you are sitting still, but you are actually hurtling at 1,600 kilometers per hour around Earth's axis, 107,000 kilometers per hour around the Sun, and 828,000 kilometers per hour around the center of the Milky Way. Standing still is something that does not exist in this universe. And stranger still, nobody, no force. Nothing flipped the switch that started all that spinning. The universe was not made to rotate. It had no other choice. If the question of why everything spins has never kept you up after this video, it will get ready. We begin. Light a piece of paper on fire, watch the smoke. It doesn't go left. It doesn't spiral. It just rises formless, directionless, dissolving into nothing. Your brain files this under chaos, and chaos, by definition, has no preferred direction, no rotation, no structure, just randomness bleeding into air. Now hold that image. Because when most people think about the Big Bang, they picture something like that: smoke, a colossal explosion, perfectly violent, perfectly symmetrical, matter spraying outward in every direction equally. A cosmic bonfire, magnificent, directionless. That picture is wrong, and the way it's wrong changes everything. If the Big Bang had been perfectly symmetrical truly, mathematically perfect, you would not exist. Not in a poetic sense, in a ruthlessly literal one. In the first fractions of a second after the universe began, matter and antimatter were produced in equal quantities. Every particle had its mirror image, and when matter meets antimatter, they annihilate each other completely, leaving behind nothing but a pulse of energy. If the early universe had been a perfect equation, balanced to the last decimal, every proton would have found its antiproton, every electron its positron. The entire contents of existence would have canceled out. No galaxies, no stars, no atoms, just light, fading into an infinite, empty dark. But we're here, sitting inside a universe full of matter, full of structure, full of spinning things, which means the equation was not balanced. Somewhere in those first moments, for every 1 billion antiparticles, there were 1,000,000,001 particles of matter, one extra. A rounding error at the scale of existence. That single unit asymmetry, that 1 in a billion imbalance, is the reason anything exists at all. And it is also the seed of every rotation in the universe. To understand how, you have to go back further than the Big Bang itself, back to the era of cosmic inflation, the first 10 to the power of -32 seconds of existence. A window of time so impossibly short it makes a billionth of a second look like a geological epoch. During inflation, the universe expanded at a rate that defies intuition. A region smaller than a proton ballooned to roughly the size of a grapefruit in an almost instantaneous burst. And during that expansion, something strange happened at the quantum level. Space was not smooth. It was never smooth. Quantum mechanics forbids it. Think of a lake on a windless morning. From a distance, it looks perfectly flat, a mirror. But get close enough, and you see it: tiny ripples, small disturbances, wrinkles that appear and vanish. The lake isn't malfunctioning. Those ripples are a fundamental property of water at that scale. Now imagine those ripples are not on water, but on the fabric of space itself. Quantum fluctuations, variations in energy density across distances of 10 to the -35 meters, roughly 100 billion times smaller than a proton, flickered in and out of existence constantly. Under normal circumstances, they would mean nothing. But cosmic inflation was not normal. As space expanded at that staggering rate, it stretched those quantum ripples out, amplified them from subatomic whispers into genuine, macroscopic variations in density. Some regions of the early universe ended up with slightly more matter, others slightly less. Not by much, not even close to much, but enough. When inflation ended and gravity began its slow work, those density variations became the blueprints. Gravity pulled matter toward the denser regions. But here's the thing, and this is the part the smoke metaphor misses entirely. Those regions didn't pull from exactly the same distance, in exactly the same direction, with exactly the same force. The matter falling inward came from slightly different positions, moving at slightly different velocities, tugged by slightly unequal forces. The collapse was never perfectly head-on. It was always, at some level, off-center. And off-center collapse produces rotation, every time, without exception. In 2018, the Planck Space Telescope team released the most detailed map of the cosmic microwave background ever produced, the faint afterglow of light left over from roughly 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form and light to travel freely for the first time. What that map showed was extraordinary in its subtlety. Across the entire sky, the temperature of that ancient light varies by only 1 part in 100,000. A difference so small that if the CMB were a piece of paper, the temperature variations would be less than 1 millimeter of height difference across the entire surface. Almost nothing. But that almost nothing is the entire architecture of the cosmos. Every galaxy cluster, every filament of the cosmic web, every spinning disk of stars you've ever seen in a photograph, all of it traces back to those temperature fluctuations in the Planck map. The structure was written in quantum noise, stretched by inflation, and then spent 13.8 billion years becoming everything. The asymmetry wasn't a flaw in the universe's design, it was the design. Which brings us to the question that sounds almost absurd once you sit with it long enough. If the universe had been just slightly more perfect, if those quantum fluctuations had been just 1 part in a million smoother, if the matter-antimatter asymmetry had been just fractionally more balanced, gravity would have had nothing to work with, no density variations to collapse, no off-center infall to generate rotation. The universe would have coasted into thermal equilibrium, a featureless, directionless fog of radiation, and stayed there forever. You would not exist to wonder why things spin. The question itself would be impossible. So the next time someone asks why everything in the universe rotates, the first honest answer is this: because the universe was born imperfect, beautifully, necessarily, life-permittingly imperfect. The chaos of the Big Bang was not directionless. It just looked that way from far enough away. Zoom in, and the imperfections were always there. Quantum mechanics guaranteed them. Inflation amplified them. Gravity inherited them. The smoke rising from a burning page looks random, but underneath it, at the level of individual molecules, there are pressure differences, temperature gradients, tiny competing forces, and those differences are what make the smoke curl the way it does. The universe is no different. The chaos was always organized. We just needed a precise enough instrument to see the fingerprints. As it turns out, our entire existence is built on a quantum imperfection smaller than an atom. A perfect universe would be an empty one. But quantum fluctuations only create difference. What actually turns that difference into organized rotation? 2 cars hit each other head-on. They stop. 2 cars clip each other at an angle, they spin. You've seen it in dashcam footage, in action movies, in parking lot, fender benders caught on surveillance cameras. The physics is immediate, intuitive. A perfectly centered collision cancels motion. An off-center collision converts it into rotation. Your brain already understands this without needing an equation. So when astronomers say rotation in the universe came from off-center interactions, the mind reaches for that car crash image. Particles smashing into each other at angles. The cosmos filled with tiny glancing blows that add up to everything spinning. Clean, logical, satisfying. Except it's not what happened. Not even close. The early universe had no cars, no solid objects of any kind. What it had for the first hundreds of millions of years was gas, specifically clouds of hydrogen and helium, so extraordinarily thin that calling them clouds feels generous. A cubic meter of this primordial material contained fewer particles than the hardest vacuum a modern laboratory can produce on Earth. There was nothing to physically collide, no surfaces to clip at an angle, no bumpers to deflect. And yet rotation emerged anyway. So the real question isn't what bumped into what. The real question is what was the cosmic equivalent of the off-center collision, operating across distances of millions of light years, in a medium so sparse it barely existed. The answer is gravity. But not gravity acting uniformly. Gravity acting on a lumpy universe. Go back to what Part 1 established: the early universe was not smooth. It was riddled with density variations, regions slightly more packed with matter, regions slightly less, all inherited from quantum fluctuations stretched out by cosmic inflation. Gravity is not democratic. It pulls harder where there is more mass. So the gas clouds forming across the early universe were not being tugged from one direction at one speed. They were being pulled from multiple directions, at multiple intensities, by an uneven landscape of gravitational attraction surrounding them. Different parts of the same cloud accelerated at different rates. Different streams of infalling gas arrived with different velocities, from different angles. And here is the crucial point: when those streams converged toward the densest region at the center of a forming structure, they almost never met at exactly the same point, moving in exactly opposite directions, perfectly canceling each other out. Almost never. The probability of a perfectly symmetric, perfectly head-on convergence across a cloud spanning millions of light years is, for practical purposes, 0. Instead, the streams missed each other slightly. Each flow carried momentum in a slightly different direction. When you add up all those slightly mismatched momenta across the entire cloud, they don't cancel. They leave a residue, a net rotation. Small, perhaps, in the beginning barely detectable, but real. And once it exists, Noether's law guarantees it persists. Pour water straight down into a funnel. It looks like it should fall through cleanly, without spinning. But the water doesn't arrive from exactly one point, with exactly one velocity. Tiny asymmetries in how you pour, microscopic friction variations along the funnel's inner surface, minuscule differences in pressure, all of it generates a slight net angular momentum. The water spirals, every time. You cannot pour it perfectly enough to prevent it? The universe was pouring gas into gravitational funnels for billions of years. The spiral was inevitable. In 2019, the illustrious TNG project, a collaboration involving researchers from institutions including MIT, Harvard, and the Max Planck Institute, published results from what was at the time the most detailed large-scale simulation of cosmic structure ever run. The simulation modeled the formation of thousands of galaxies across a volume of space, roughly 300 million light-years on each side, tracking the behavior of dark matter, gas, stars, and magnetic fields simultaneously. One of its findings was quietly remarkable. Even galaxies that formed in regions of the simulated universe that were, by design, as smooth and featureless as the team could make them isolated from obvious external torques. Far from major filaments and cluster interactions, still developed angular momentum. Every single one. The reason was Heisenberg's uncertainty principle. In quantum mechanics, you cannot simultaneously know the exact position and exact momentum of a particle with perfect precision. The universe itself enforces this ignorance not as a limitation of measurement, but as a fundamental feature of reality. This means that at the quantum scale, perfect smoothness is not just unlikely, it is physically forbidden. Density fluctuations exist, because they must. They cannot be engineered away. And those unavoidable fluctuations, however microscopic, feed into gravitational collapse, which feeds into off-center infall, which feeds into rotation. The illustrious TNG result was not a surprise to theorists, but it was a confirmation there is no scenario, however idealized, in which gravity operates on quantum matter and rotation fails to appear. Rotation is not a feature of some cosmic objects. It is what matter does, universally, when gravity gets involved. You might be sitting with an objection right now, and it's a sharp one. If everything in the universe spins, why doesn't everything spin the same way? Galaxies rotate clockwise and counterclockwise in roughly equal proportions. Some planets orbit counterclockwise when viewed from above the solar system's north pole. Others, like Venus, rotate backward on their own axes entirely. Uranus spins tipped almost completely on its side, its axis tilted 97.77 degrees from vertical. The universe looks, from this angle, profoundly uncoordinated. Exactly right, and that's the point. There is no preferred direction of rotation embedded in the laws of physics, and you already know why. From what was established about Noether's theorem in Part 1, rotational symmetry means no direction is special. So, the net angular momentum that develops in any given collapsing cloud depends entirely on the local configuration of density fluctuations in that particular patch of space. Turn left or right randomly enough times, and the results are random. The universe generated rotation everywhere, but which way anything spins is a local accident of initial conditions, not a cosmic preference. The disorder of spin directions is not a flaw in the theory. It is direct evidence that the theory is correct. The universe has no tidiness instinct. It did not sit down and design a rotation scheme, assign directions, issue angular momentum permits. It simply allowed gas to fall toward gravity under conditions that quantum mechanics guaranteed would never be perfectly symmetric, and rotation fell out the other side, as inevitably as water spiraling in a drain. Humanity invented the wheel not because someone had a flash of geometric genius, but because rolling requires less effort than carrying. The universe arrived at rotation for essentially the same reason, not through intention, but because the path of least resistance, when asymmetric matter falls toward gravity, is to spin. The wheel was always the obvious answer. It just took us a few 100,000 years to notice. The universe noticed immediately. Or rather, it had no choice but to notice. But when a gas cloud begins to spin, an iron law appears, a law that not even the universe can violate. Watch a figure skater, arms spread wide, rotating slowly one lazy revolution every couple of seconds, almost meditative. Then she pulls her arms inward, tight against her chest, and instantly, almost violently, she accelerates into a blur. No external push, no additional energy input, just a change in shape, and the universe responds by multiplying her speed. Everyone has seen this. Almost no one has asked why, not how the mechanics are taught in high school physics. But why does the universe insist on remembering her rotation when she changes her shape? Why doesn't some of that spin simply dissipate, the way heat leaks out of a coffee cup or sound fades in an open field? What is doing the remembering, and where does that obligation come from? The answer is not in any physics equation. It lives deeper than that. It lives in pure mathematics. And it was proved by a woman whose name most people don't know, in a year when she wasn't officially allowed to hold an academic position. 1915, Emmy Noether, working at the University of Göttingen in Germany, published what would become one of the most consequential theorems in the history of human knowledge. Einstein, upon reading it, wrote that Noether was the most significant creative mathematical genius thus far produced. not the most significant female mathematician, the most significant mathematical genius. Full stop. The theorem stated every continuous symmetry of a physical system corresponds to a conserved quantity, 1-to-1. No exceptions anywhere in nature. Take that apart carefully, because each word is doing real work. A symmetry, in physics, means something that remains unchanged under a transformation. Time symmetry means the laws of physics are the same today as they were yesterday and will be tomorrow. The rules don't drift as the clock advances. Noether's theorem connects that symmetry directly to conservation of energy. Translational symmetry means the laws of physics work identically here, in the next city, on a planet orbiting a star 40 light-years away. Changing your location doesn't change the rules. That symmetry connects directly to conservation of linear momentum. And rotational symmetry, the symmetry that no direction in space is privileged, that the laws of physics operate identically regardless of which way you face, connects directly to conservation of angular momentum. Think carefully about what this means. The figure skater's rotation is preserved not because of some sticky property of spinning, not because physics has a special fondness for rotation. It's preserved because space itself has no preferred direction. The universe is at a deep geometric level, rotationally indifferent, and it is precisely that indifference, that perfect structural impartiality, that makes angular momentum untouchable. Construct the alternative. Imagine a universe with a special direction, call it cosmic north. The laws of physics in this hypothetical universe behave slightly differently, depending on whether you orient your experiment toward cosmic north or away from it. Rotational symmetry is broken, and the moment that symmetry breaks, Noether's theorem says conservation of angular momentum breaks with it. Spinning objects in that universe could spontaneously slow down, their rotation bleeding off into the preferred direction, the way a compass needle swings toward magnetic north. Orbits would be unstable. Galaxies couldn't maintain their disks. Everything we observe about the large-scale structure of the cosmos would be impossible. Our universe is not that universe. No experiment, not one, across the entire history of science has detected a preferred direction in space. The rules are the same in every direction, so angular momentum is conserved, not as a choice, not as a rule imposed from outside, as a geometric inevitability written into the fabric of space itself. To make this concrete, imagine you're playing poker, and the rules change based on which direction you face at the table. A flush beats a full house when you face east, but not when you face west. That's a universe without rotational symmetry. In our universe, poker rules and all rules are the same regardless of orientation. No direction is special. And that sameness is what locks angular momentum in place. How precisely does it hold? Experiments at CERN, testing the conservation laws underlying rotational symmetry, have confirmed angular momentum conservation to an accuracy of 1 part in 10 to the power of 14. Write that out, 1 in 100 trillion. To make that number tangible, if you measured the distance across the continental United States, roughly 2,800 miles, with that precision, your margin of error would be smaller than a single atom's diameter. Across 13.8 billion years of cosmic history, no exception has ever been recorded. Not one measurement, not one observation, not one anomaly suggesting that angular momentum appeared from nothing or vanished into nothing. It is, as far as every instrument humanity has built can determine, a perfect law, absolute, without loophole. This places it in a different category from most physical laws, which admit approximations, edge cases, limiting conditions. Angular momentum conservation does not negotiate. And now, the abstraction becomes something you can feel. The Earth beneath you right now completes one full rotation every 23 hours, 56 minutes, and 4 seconds. It has maintained this through the formation of continents, through mass extinctions, through the rise and fall of every civilization in human history for 4.5 billion years. Not because anything keeps pushing it, because a collapsing cloud of gas and dust 4.5 billion years ago carried a net angular momentum, and that momentum was compressed as the cloud shrank, transferred to the protoplanetary disk, inherited by the forming Earth, and preserved without a single unit, lost through every subsequent event in the solar system's history. Every rotation of the Earth today is a direct inheritance from that original spinning cloud. The angular momentum that tips you from Tuesday into Wednesday morning was encoded in the structure of the early solar system before the sun ignited. You are, at this moment, riding angular momentum that is 4.5 billion years old. The skater pulls her arms in. The nebula collapsed. Different scales, same law, same universe, without memory lapses. Emmy Noether was denied a faculty position at Göttingen in 1915 because she was a woman. The University Senate reportedly objected on the grounds that female professors were inappropriate. David Hilbert, arguably the greatest mathematician of the era, responded with barely concealed contempt for the objection. He pointed out that the university was not a bathhouse and that the candidate's gender was irrelevant to the quality of her mathematics. He allowed her to lecture, but only under his own name. Her work circulated. Her credit, officially, did not. The universe, operating on her theorem, has never noticed the distinction. It conserves angular momentum with the same perfect reliability, regardless of who derived the proof. The cosmos has no bureaucratic hierarchy, no credentialing committee. It just follows the math. The universe has no gender bias. People, as it turns out, do. The figure skater pulls her arms in and spins faster, but what happens when an entire nebula, spanning billions of kilometers, pulls itself in? Watch a pizzaiolo toss dough. The ball leaves his hands spinning at a moderate pace, arms extended wide, releasing at the outer arc of the throw. As the dough rises, it spreads outward under its own centrifugal force, the diameter growing, the spin visibly slowing. Then he catches it, compresses it back, draws it inward, and the rotation quickens again. Every pizzeria in America is running an informal physics demonstration every single day. The relationship is immediate, physical. Something you can see with your own eyes more spread out means slower rotation. More compact means faster. The size and the speed trade against each other. Always. That trade-off has a name. It is conservation of angular momentum, and it operates at every scale the universe contains. Now hold that image of the expanding dough and scale it up by a factor that breaks intuition entirely. The nebula that eventually collapsed to form our solar system stretched across a diameter of more than 65 billion kilometers. Not 65 billion miles. Kilometers. To put that in a frame, your brain can work with the current distance between Earth and the Sun is roughly 150 million kilometers. The solar nebula was more than 400 times wider than that gap, a cloud so vast that light, traveling at 300,000 kilometers per second, would have taken over 60 hours just to cross it. This cloud was rotating, slowly, almost absurdly slowly. According to the updated NICE model simulations published in 2021, the initial rotation rate of the pre-solar nebula was approximately 1 full revolution every few million years, millions of years per rotation. If you were somehow watching this cloud from outside the solar system in its earliest stage, you would see nothing moving at all on any human timescale. Then gravity took hold. The cloud began to collapse inward, and conservation of angular momentum, Noether's unbreakable law, did what it always does when radius shrinks. It made the speed pay for the compression. By how much the sun, the compressed remnant of that original nebula's core, now completes one full rotation every 25 days at its equator. The Earth, assembled from the disk of leftover material orbiting that collapsed core, rotates once every 24 hours. From millions of years per revolution to 24 hours per revolution, the increase in rotational speed across the collapse of the solar nebula is not 10 times, not 1,000 times. The compression factor in terms of radius alone was on the order of tens of thousands. And since rotational velocity scales with the inverse square of the radius, the speed amplification across the full collapse reaches into the billions of times faster. From the same angular momentum, not one unit created from nothing, not one unit destroyed, just compressed. The mechanism deserves a clearer picture, because the mathematics without imagery is just symbols. Angular momentum, call it L, equals the moment of inertia multiplied by the angular velocity. Moment of inertia, in plain language, is a measure of how spread out the mass is from the axis of rotation. A basketball spinning on one finger has a certain moment of inertia. Now imagine that same basketball inflated to the diameter of the Earth's same mass, same spin rate, but the mass is distributed across an incomparably larger radius. The moment of inertia would be staggering. To maintain that spin against the laws of conservation, you'd need an equally staggering amount of angular momentum input. But run it the other way. Start with the Earth-sized basketball spinning lazily, then compress it back to normal basketball size. You haven't added a single unit of angular momentum. You've just shrunk the radius, and the velocity has no choice but to multiply. The universe doesn't charge you for the speed increase. It gives it to you automatically. For free, as the geometric consequence of becoming smaller. This is what happened to the solar nebula. Gravity compressed it. The compression was free. The speed came with it. There was no committee meeting, no decision made by any authority about how long a day should be. The length of Earth's rotation, 24 hours, the rhythm that organizes every human schedule, every time zone, every morning alarm, was set 4.6 billion years ago by the rate at which a specific cloud of gas and dust collapsed under its own gravity in a specific arm of the Milky Way. The collapse rate determined the final angular velocity. The angular velocity, preserved without loss, became the spin of the protoplanetary disk. The disk's spin became the rotation of the forming Earth, and the Earth's rotation became the framework inside which every human civilization has ever organized its time. 24 hours in a day, time zones sliced across continents, work schedules, school bells, the timing of your morning coffee, all of it traces back in an unbroken causal chain to the collapse dynamics of a gas cloud 4.6 billion years ago. The NICE model originally developed in Nice, France, in 2005 and substantially updated through 2021 with new constraints from observations of exoplanetary systems and trans-Neptunian objects, remains the leading framework for understanding how the outer solar system reached its current configuration. Its simulations reproduce the orbital architecture of the giant planets, the structure of the Kuiper belt, and the rotation rates of the inner planets with remarkable accuracy. The angular momentum budget of the entire solar system, distributed among the Sun and its planets in the proportions we observe, falls naturally out of the collapse dynamics the model describes. The model didn't decide these outcomes. It revealed that the outcomes were always implicit in the initial conditions. The physics made the choices. Gravity did the work. Angular momentum kept the books. You had no vote on the length of your day. No appeal process exists. The universe set the schedule 4.6 billion years before your species existed, through a process you couldn't have influenced even in principle. Sunrise, sunset, the number of hours available to work or sleep or stare at the ceiling, wondering about astrophysics, all determined by a collapsing gas cloud in the early Milky Way. There was no meeting, The universe didn't consult anyone. It just collapsed, conserved, and handed you a 24-hour day as a fait accompli. You are not allowed to complain about it. Angular momentum conservation does not have a feedback form. Rotation is not just the result of collapse. It is the reason everything doesn't keep collapsing. Swing a bucket of water over your head. The water stays in the bucket. At the top of the arc, the bucket is inverted. Gravity is pointing straight down toward the water's surface, and nothing spills. The centrifugal effect of the circular motion pushes the water outward, pinning it to the bucket's base even when the bucket is upside down. Every child who has ever tried this at a physics demonstration and then learned to deeply regret slowing down too soon understands the basic principle: rotation generates an outward push that can counteract the inward pull of gravity. Most people accept this as a fun trick of physics, a novelty. They file it under things that seem weird but have an explanation and move on. Almost nobody asks the follow-up question. And the follow-up question is the one that changes everything. If centrifugal force didn't exist, if rotation produced no outward push whatsoever, where would the planets be right now? Not in some slightly different orbit, not marginally closer to the sun, gone, consumed. Every planet in the solar system, including Earth, would have spiraled inward and been swallowed by the sun within a geologically trivial period of time after the solar system formed 4.5 billion years ago. The ground beneath you exists and has existed for 4.5 billion years, not because it was placed safely in space, but because it is moving continuously at exactly the right speed to keep falling without ever arriving. This is not a poetic description. It is the literal mechanical reality of what an orbit is. Newton understood this, and the story is more interesting than the famous Apple version usually told. Yes, Newton watched something fall. But the thought that crystallized his understanding of gravity and orbital mechanics was not about the apple hitting the ground. It was about the moon. He asked, why doesn't the moon fall? It is subject to Earth's gravity? He could calculate that. Gravity should pull it inward. Why does it stay up? His answer was that the moon is falling. It falls toward Earth continuously, but it is also moving sideways tangentially, parallel to Earth's surface fast enough that by the time it has fallen a certain distance toward Earth, the Earth's surface has curved away by the same distance beneath it. The moon perpetually falls toward a surface that perpetually curves away. It never arrives. That is an orbit. He then imagined a cannon on a very tall mountain, tall enough to place the cannonball above the atmosphere, eliminating air resistance. Fire the cannonball with a small charge, it arcs and hits the ground nearby. Fire it harder, it lands farther away. Fire it hard enough at approximately 7.9 kilometers per second, and the cannonball falls toward Earth's curved surface at exactly the rate the surface curves away. The cannonball is now in orbit. It is always falling. It never lands. Every satellite in orbit above Earth right now, every space station, every planet around every star is executing the same maneuver, falling, continuously, with exquisite precision. Now consider what happens if the sideways motion stops. If Earth's orbital velocity, currently 29.8 kilometers per second, were somehow instantaneously reduced to zero, Earth would cease to orbit. Gravity, suddenly unopposed by any tangential velocity, would pull it directly inward along a straight line toward the sun. The journey from Earth's current orbital distance to the sun's surface, in pure freefall with no orbital component, would take approximately 64.5 days. Not millions of years, not thousands, 64.5 days. In just over 2 months, the planet would be gone. Every ocean, every continent, every organism incinerated as Earth plunged into the solar photosphere. The margin between existence and annihilation is not a vast gulf of time. It is the difference between moving at 29.8 kilometers per second and not moving at all. The solar system is not a safe storage arrangement. It is a dynamic equilibrium, maintained at every moment by the angular momentum of objects that are, technically, perpetually falling. Remove the motion, and the structure collapses within weeks. The same logic extends upward in scale without limit. Stars in a galaxy are not sitting still, held in place by galactic gravity like marbles in a bowl. They orbit the galactic center, their tangential velocities balancing the gravitational pull of hundreds of billions of other stars and the enormous halo of dark matter surrounding the disk. Remove that orbital motion, extinguish the angular momentum of every star simultaneously, and the Milky Way, 100,000 light-years across and containing an estimated 200 to 400 billion stars, would collapse into its central region within a timescale that, astronomically speaking, would be essentially instantaneous. The galaxy exists as a galaxy because it spins. Its structure, its arms, its disk, all maintained by the same principle that keeps water in a bucket overhead and Earth from plunging into the sun. Technically speaking, orbit is the most elegant way to fall that physics permits. Earth is not flying through space. It is not hovering, not floating, not suspended. It is falling in the most controlled, sustained, geometrically perfect manner possible, at a velocity calibrated by 4.5 billion years of gravitational dynamics to keep it precisely equidistant from destruction. The planet is not safe. It is just falling correctly. Very, very stylishly. Centrifugal force doesn't just keep planets in orbit, it also determines the shape of the entire universe. Watch someone toss pizza dough. A ball of dough, round, compact, three-dimensional, launched upward with a spin. Within seconds, it transforms. The centrifugal force of rotation pulls the dough outward from its center, stretching it laterally, flattening it progressively from a sphere into a disk. Nobody is pressing it flat. No rolling pin is involved. The spin itself is doing the work, and gravity keeps the whole thing from simply flying apart into separate pieces. The result? A thin, flat circle. Every time, without exception. Nobody standing in a pizzeria thinks about galaxies. But they should, because that is precisely not approximately, not metaphorically, but precisely the same physical mechanism responsible for the Milky Way, for the protoplanetary disk that formed our solar system, for the rings of Saturn, for every flat disk-shaped structure at every scale in the observable universe. The dough and the galaxy are obeying identical equations. The only difference is the numbers. So why does the universe have such an overwhelming preference for the disk shape? Why, out of all the three-dimensional forms that rotating matter could theoretically settle into, does it so consistently produce flat, thin, spinning plates? The answer comes down to a competition between two directions and the fact that rotation only pushes back in one of them. When a cloud of gas and dust begins rotating and then contracts under gravity, centrifugal force does not push outward in all directions equally. It pushes outward only in the plane perpendicular to the rotation axis, the equatorial plane, the belt around the cloud's middle, along the axis of rotation itself. Vertically relative to that belt, centrifugal force does nothing. Gravity, pulling inward from all directions toward the center of mass, acts along the vertical axis completely unopposed. The result is a directional asymmetry in the collapse. Vertically parallel to the rotation axis, gravity wins without contest. The cloud collapses rapidly in that direction, its vertical extent shrinking as matter falls toward the equatorial plane. Horizontally perpendicular to the rotation axis, centrifugal force pushes back hard enough to halt or slow the inward collapse. Depending on the rotation speed, matter in the equatorial plane spreads outward, or at minimum, resists further inward compression. The outcome is geometrically inevitable. Compress a sphere from the top and bottom, while simultaneously preventing the middle from compressing. You get a disk. The cloud flattens. Not because anyone designed it that way. Because gravity and centrifugal force are having two completely different conversations along two completely different axes simultaneously, and the disk is the only shape that satisfies both arguments at once. Think again about the pizza dough. Rotation pulls the dough outward laterally, centrifugal effect stretching the circumference. Gravity pulls the dough downward, preventing it from expanding vertically, keeping it thin. The dough cannot simultaneously expand sideways and also maintain height. Something has to give. What gives is the vertical dimension. The dough thins. The same physics, operating at vastly different scales, produces the same geometry. Now apply numbers to this, because the numbers are where the story becomes genuinely strange. The Milky Way is approximately 100,000 light-years in diameter. If you could travel at the speed of light, 300,000 kilometers per second, it would still take you 100,000 years to cross from one side to the other. By any human measure, it is incomprehensibly large. Its thickness. The thin disk, the region where most of the Milky Way's stars, gas, and dust reside, is approximately 1,000 light-years deep. 1,000 against 100,000. A ratio of 1 to 100. Scale that ratio down to something you can hold. Take a standard sheet of printer paper. Its diameter is about 28 centimeters across. Its thickness is approximately 1/10 of a millimeter. The ratio of diameter to thickness for a sheet of printer paper is roughly 2,800 to 1. The Milky Way's ratio is 100 to 1. The galaxy is, proportionally speaking, significantly thicker relative to its diameter than a sheet of paper, but still 100,000 light-years wide, 1,000 light-years thick. The galactic disk is, by any intuitive measure, extraordinary thin for its width. And the protoplanetary disk that formed our solar system had a comparable aspect ratio wide, flat, impossibly thin relative to its diameter. This is not coincidence. Both structures formed by the same mechanism, both obeying the same physics, both arriving at disk geometry for the same fundamental reason. The aspect ratio is the fingerprint of the process. You might be constructing a counter-argument right now, and it's a reasonable one. The universe contains structures that are emphatically not disks. Elliptical galaxies, some of the most massive objects in the cosmos, are roughly spherical or ellipsoidal, not flat. Dark matter halos surrounding galaxies are roughly spherical. Stars themselves are spheres. Globular clusters are spheres. The universe clearly does not produce only disks. Correct. But the distinction is angular momentum. Structures with low angular momentum collapse toward spheres. Gravity pulls inward symmetrically, and without sufficient rotation to create the equatorial asymmetry, the collapse is roughly equal in all directions. Elliptical galaxies are thought to have formed through major mergers of spiral galaxies, where the angular momenta of the merging systems partially canceled out, leaving a remnant with much lower net rotation. Dark matter halos are approximately spherical because dark matter interacts only gravitationally and cannot dissipate energy the way gas does, so it never settles into a disk regardless of its angular momentum. But any structure with sufficient angular momentum, any rotating system that can also dissipate energy through collisions and radiation among its constituent particles, will naturally evolve toward a disk. It is the minimum energy configuration for a given angular momentum. The disk is not one option among many. It is the destination. The universe didn't invent the disk shape when humans first threw bread dough into the air. It had been producing disks for 13 billion years by then. We just rediscovered the geometry and added tomato sauce. Saturn's rings make the point with particular clarity. They span roughly 280,000 kilometers in diameter, wider than the distance between Earth and the Moon. Their thickness ranges from approximately 10 meters to 1 kilometer in different regions. The ratio of diameter to thickness is, in places, comparable to a sheet of paper scaled up to the size of a city block, the most dramatic disk structure in our solar system, produced by exactly the mechanism described: rotation, providing equatorial support, gravity providing vertical confinement, the disk as the inevitable geometric compromise. Every flat thing you see in the cosmos, every spiral galaxy photograph, every artist's impression of a planetary system, every image of Saturn's rings is the same story. Rotation resisting gravity in one plane, gravity winning in the other, disk as the resolution. The universe has exactly one answer when you ask what shape spinning matter settles into. It has been giving that same answer for 13 billion years. We just weren't paying attention until recently. Rotation creates shape, but it also distributes energy in ways so strange that even the Moon is affected. Common sense says the heaviest thing owns the most of everything. The Sun contains 99.8% of all the mass in the solar system. Every planet, moon, asteroid, comet, and drifting particle of dust combined accounts for the remaining 0.2%, a rounding error against the Sun's overwhelming gravitational dominance. By any intuitive measure, the Sun should be the solar system's center of gravity, center of power, and center of angular momentum. It should own the spin. It has almost everything else. It doesn't. The Sun accounts for approximately 0.5% of the solar system's total angular momentum, 0.5%. The entity containing 99.8% of the mass holds less than 1% of the spin energy. The remaining 99.5% of angular momentum is distributed among the planets, and of that planetary share, Jupiter alone holds approximately 60% of the total solar system angular momentum. Jupiter, a planet with a mass roughly 1/1000th of the Sun's, a planet that, by mass fraction, is almost invisible in the solar system's accounting. Yet it carries 60% of all the rotation energy in the entire system. If angular momentum were wealth, Jupiter would be the billionaire. The Sun would be on a salary. How is this possible? The answer lies in the formula for angular momentum, and specifically in which variable does the most work. Angular momentum for an orbiting body equals its mass multiplied by its orbital velocity, multiplied by its orbital radius, the distance from the center of the system. Mass matters, velocity matters. But radius matters in a way that mass and velocity cannot easily compensate for, because radius is the lever arm. The farther from the axis, the greater the contribution to angular momentum, regardless of how heavy the object is. Think about a merry-go-round. A small child sitting at the outer edge of the platform will require significantly more force to stop the rotation than a heavier adult sitting at the center, because the child's distance from the axis multiplies their contribution to the system's angular momentum far beyond what their weight alone would suggest. The adult at the center, despite being heavier, has a short lever arm. The child at the edge has a long one. The lever arm wins. Jupiter orbits the Sun at an average distance of approximately 778 million kilometers, more than 5 times the Earth-Sun distance. It moves along that vast orbit at approximately 13 kilometers per second. Multiply mass by velocity by radius, and Jupiter's angular momentum dwarfs the Sun's rotational angular momentum by a factor of roughly 20 to 1. The Sun spins at its location. Jupiter orbits at an enormous distance. Distance dominates. This creates a problem that has occupied astrophysicists since the 1960s, when it was first precisely quantified. It is called the angular momentum problem of star formation, and it remains an active research topic to this day. The problem when a molecular cloud collapses to form a star. Conservation of angular momentum should cause the resulting star to spin extraordinarily fast. The cloud's angular momentum must go somewhere. If it all concentrates in the central protostar, the star should be rotating near its breakup velocity, the speed at which centrifugal force at the equator would overcome surface gravity, and the star would fly apart. Real young stars do rotate faster than older ones, but nowhere near breakup velocity. And our Sun, a middle-aged star, rotates at a relatively leisurely rate, one revolution every 25 days at the equator. The angular momentum went somewhere. But where? The leading current explanation involves magnetic fields and protostellar winds. During the early formation of the Sun, when it was still a young protostar embedded in its surrounding disk, its magnetic field lines threaded outward through the disk material. As the disk rotated, the magnetic field acted as a coupling mechanism, transferring angular momentum outward from the protostar into the outer disk material through a process called magnetic braking. The inner protostar slowed down. The outer disk material spun up. Angular momentum migrated outward across the magnetic field lines like current flowing through a wire. Over millions of years, as the disk material in the outer regions accreted into the giant planets, Jupiter foremost among them, that outward transferred angular momentum became locked into Jupiter's vast orbital motion. The Sun shed its excess spin. Jupiter inherited it. The current distribution is the fossilized record of that ancient transfer. Consider the chain of consequences if Jupiter did not exist in its current position or did not exist at all. The angular momentum that Jupiter now carries in its orbital motion would have had nowhere to go. It would have remained in the inner system, concentrated in the Sun's rotation. A faster spinning Sun emits more energetic particle radiation in its early life, bathes the inner planets in more intense stellar wind, and generates a more volatile magnetic environment. Whether Earth's atmosphere and surface could have stabilized into a life-permitting state under those conditions is genuinely uncertain. The detailed modeling is complex, and the question remains open, but the direction of the effect is not more angular. Momentum in the Sun means a more active, more disruptive young Sun and a harder road to habitability for the third planet. Jupiter is not merely a large object in the outer solar system, irrelevant to life on Earth. It is a reservoir of angular momentum that absorbed the Sun's excess spin during formation, stabilized the Sun's early rotation rate, and in doing so, contributed indirectly, through a chain of physical consequences, to the conditions that allowed Earth to become what it is. Jupiter's philosophy, if a gas giant could have one size, is optional. Distance is everything. Angular momentum is distributed, and it is also stolen over time. The first victim Earth's own rotation. The Moon always shows the same face to Earth. Everyone knows this. It's one of those facts absorbed in childhood, filed away, never questioned. The near side, the one with the seas and the craters that ancient humans turned into rabbit shapes and human profiles, permanently faces us. The far side, famously called the dark side, though it receives just as much sunlight, permanently faces away. The Moon presents itself to Earth like a portrait that never turns. Most people accept this as simply how the Moon is. Almost nobody asks what it cost us. Earth is slowing down. Not dramatically, not in any way you would notice across a human lifetime, but measurably, precisely, inexorably, the planet's rotation is decelerating. Every century, the length of a day grows by approximately 1.7 milliseconds. A millisecond is 1,000th of a second. 1.7 of them per 100 years sounds trivial, the kind of number that belongs in a footnote rather than a revelation. Run that number backward across geological time and the trivial becomes staggering. 4.5 billion years ago, when Earth was newly formed, still hot from accretion, its surface a churning ocean of magma. A day on Earth lasted approximately 6 hours. Not 24, 6. The planet was spinning roughly 4 times faster than it does today, completing nearly 4 full rotations in the time it now takes to complete one. The earliest microbial life on Earth, single-celled organisms clinging to existence in shallow coastal waters more than 3 billion years ago, lived their entire existence within a 6 to 10 hour day. Every biological rhythm, every chemical cycle, every process that eventually led through billions of years of evolution to the organisms alive today ran inside a radically shorter rotation period. The 24-hour day you experience is not a fixed property of Earth. It is a snapshot in the middle of a long deceleration, and the engine driving that deceleration is sitting in the sky, 384,000 kilometers away. The mechanism is subtle and relentless. The moon's gravity doesn't pull on Earth uniformly. It pulls harder on the side of Earth facing the moon and weaker on the far side. This differential pull distorts Earth's oceans into a slight, elongated shape, creating 2 bulges, one on the side facing the moon, one on the opposite side. These are the tidal bulges, the source of high and low tides as Earth rotates beneath them. Here is the critical detail. Earth rotates faster than the moon orbits around it. The moon takes approximately 27.3 days to complete one orbit. Earth completes a full rotation in roughly 24 hours. So Earth is spinning underneath the moon much faster than the moon moves overhead. As a result, Earth's rotation drags the tidal bulge slightly ahead, not directly beneath the moon, but displaced forward in the direction of Earth's rotation. That displaced bulge has mass. Mass has gravity. The gravitational pull of the leading tidal bulge tugs backward on Earth's rotation, a constant, gentle braking force applied through the friction between ocean water and the sea floor as the tides ebb and flow. The ocean is, in effect, a brake pad pressing against the planet's spin. Conservation of angular momentum demands the accounting be balanced. The angular momentum that Earth loses from its spin doesn't vanish. It transfers to the moon through the gravitational interaction. The moon, receiving this angular momentum, accelerates in its orbit. An object that accelerates in orbit moves to a higher orbit. The moon drifts outward. Push someone who is spinning your effort goes into their motion, and they move away from you. Same principle, different scale by a factor of roughly 10 to the 22nd power. In 1969, the Apollo 11 crew placed a retroreflector on the lunar surface, a panel of corner cube prisms designed to bounce laser light directly back to its source with extraordinary precision. Additional reflectors were left by Apollo 14 and 15, and by the Soviet Luna 17 and 21 missions in 1970 and 1973 respectively. For more than 50 years, observatories around the world have been firing laser pulses at these reflectors and measuring the round-trip travel time to millimeter precision. The result is unambiguous. The moon is moving away from Earth at a rate of 3.8 centimeters per year, not approximately, not as an estimate, 3.8 centimeters per year, measured directly, confirmed across decades of laser-ranging data. The angular momentum transfer is not theoretical. It is observed, quantified, and ongoing. Now extend that trajectory forward. In approximately 600 million years, the moon will have receded far enough that its apparent diameter in Earth's sky will no longer be sufficient to cover the sun's disk during a solar alignment. Total solar eclipses those extraordinary minutes when the moon fits almost impossibly perfectly over the sun. Revealing the corona in a ring of fire around a black disk will cease to be possible. The geometry will no longer work. The moon will be too small in the sky, the sun too large relative to it. Every total solar eclipse that has ever occurred in human history, every one that ancient civilizations interpreted as divine intervention, every one that allowed 19th century astronomers to study the solar corona, all of them exist only because we happen to live at this specific moment in Earth-Moon history. when the sizes match. 600 million years from now, that window closes permanently. The generation alive today, and perhaps the next 100 generations, will have the opportunity to experience total solar eclipses. After that, not the gradual degradation of the phenomenon, but its complete end. The moon will still orbit, the sun will still shine, but the geometry of perfect overlap will be gone, transferred away millisecond by millisecond through the friction of ocean tides. We are living in a narrow window of cosmic coincidence. Nobody can buy more time in this window. Angular momentum doesn't negotiate. The tides will keep breaking. The moon will keep receding. The eclipses will eventually stop. The moon has been stealing our day 1.7 milliseconds per century for 4.5 billion years. It is the slowest theft in the history of the solar system, carried out with no intent, no malice, and no possibility of legal recourse. The conservation law is the accomplice, and it has never once testified against the defendant. If the moon is slowly breaking Earth 1/fraction of a millisecond at a time, what happens when conservation of angular momentum is not slowed down, but amplified to its absolute extreme? The figure skater pulls her arms in and spins faster. You know this. You have seen it? Perhaps understood the principle? Perhaps filed it away as a pleasing demonstration of physics. But ask the obvious follow-up. Does this have a limit? Can she pull her arms in indefinitely and spin indefinitely faster? Of course not. Her body has a physical limit, the structural integrity of human tissue, the maximum rotational stress her muscles and bones can sustain. At some point, the physics of her body overrides the physics of angular momentum conservation. She stops accelerating. She steps off the ice. What if there were no such limit? What if you could compress a rotating object without any material constraint, collapsing it, not just to a tighter configuration, but to a fraction of a percent of its original size? What does conservation of angular momentum do then? The universe has a laboratory for this question. It is called a neutron star, and the answer it provides is almost too extreme to process. Stars between approximately 8 and 20 times the mass of the Sun end their lives in core collapse, supernova, catastrophic explosions that release more energy in a few seconds than the Sun will emit across its entire 10 billion year lifetime. When the outer layers blast outward in the explosion, the core collapses inward under gravity with nothing to stop it. The nuclear fusion that had been generating outward pressure for millions of years ceases. Gravity wins, instantly and completely. What remains is a neutron star. The original stellar core, which may have spanned several 100,000 kilometers in diameter, collapses to an object roughly 20 to 25 kilometers across. Not 20 to 25,000 kilometers, 20 to 25 kilometers. The radius shrinks by a factor of approximately 100,000. Apply conservation of angular momentum to a radius compression of 100,000. Angular velocity scales with the inverse square of the radius. Shrink the radius by 100,000, and rotational speed increases by the square of 100,000 10 billion. A star that was rotating once every few weeks before collapse can emerge from the supernova spinning hundreds of times per second. The fastest neutron star ever measured is the pulsar designated PSRJ 1748-24446 AD. Located in a globular cluster approximately 18,000 light-years from Earth, its rotation rate 716 revolutions per second, 716 complete rotations every second. The equatorial surface of this object moves at approximately 24% of the speed of light. Not a fraction of a percent, not a few percent, nearly 1/4 of the cosmic speed limit, sustained continuously in a solid object roughly the size of a city. The natural question, why doesn't it fly apart? At that rotational velocity, The centrifugal stress on the equatorial surface is almost incomprehensible. For any ordinary material, steel, rock, anything built from atoms as we understand them, that stress would exceed the binding strength of matter by orders of magnitude. The object should disintegrate. It doesn't, because neutron star material is not ordinary matter. Inside a neutron star, the density is so extreme that electrons and protons are crushed together into neutrons, the same particles that occupy atomic nuclei, but now packed together at nuclear density across the entire object. The strong nuclear force, which normally operates only at subatomic distances within individual nuclei, effectively governs the entire structure. The neutron degeneracy pressure, a quantum mechanical resistance to further compression arising from the Pauli exclusion principle, which forbids two neutrons from occupying the same quantum state, provides the structural integrity that prevents collapse into a black hole. To make the density concrete, a single teaspoon of neutron star material, scooped from its interior, would weigh approximately 10 million metric tons. Not 10 million kilograms, 10 million metric tons. Placed on Earth's surface, that teaspoon would sink through the crust, the mantle, and the core, exiting through the other side and oscillating for a period before settling at the center of the planet. If Earth itself, the entire planet, all 6 times 10 to the 24th kilograms of it, were compressed to neutron star density, it would fit within a sphere approximately 300 meters in diameter, smaller than the length of 3 American football fields. The discovery of neutron stars came as a complete surprise and almost wasn't recognized for what it was. In 1967, a graduate student named Jocelyn Bell Burnell, working at the Mullard Radio Astronomy Observatory in Cambridge under Anthony Hewish, detected an unusual signal in her radio telescope data pulses of radio waves arriving with extraordinary regularity, repeating every 1.3373 seconds without variation. The precision was so remarkable that the research team initially designated the source LGM, one little green men, as a half-serious placeholder, because no known natural phenomenon produced signals that regular. The possibility of an artificial, extraterrestrial origin was briefly, genuinely considered. What Bell Burnell had discovered was a rotating neutron star, a pulsar sweeping its beam of radio emission across Earth with each rotation, like a cosmic lighthouse. The regularity was not the product of intelligence. It was the product of conservation of angular momentum applied to an object so dense and so rapidly spinning that its rotation rate was stable to within fractions of a nanosecond per rotation. The Nobel Prize in Physics was awarded in 1974 for the discovery of pulsars. It went to Anthony Hewish and Martin Ryle. Jocelyn Bell Burnell, who made the actual observation and initially identified the anomalous signal, was not included. The physics community has debated the omission ever since. Bell Burnell herself has responded to the controversy with a grace that most would find impossible to summon. 716 rotations per second. Sit with that for a moment. A typical human breath, one full inhalation, takes approximately 3 to 4 seconds. In the time it takes your lungs to expand with air, PSRJ 174-8 T-2 and 6 AID completes more than 2,000 full rotations around its own axis. Not oscillations, not partial turns. 2,000 complete revolutions of a solid object 25 kilometers across in the duration of a single breath. If that neutron star competed in any Olympic sport involving rotation, the organizing committee would need to create an entirely new category and institute a permanent ban on any competitor made of carbon-based matter. The podium would be uncontested and, frankly, terrifying. A neutron star is the extreme limit of ordinary matter, but there is something beyond it, where rotation no longer just affects matter, but twists the structure of space-time itself. pull a wooden stick through water. Watch what happens around it. The water immediately adjacent to the stick doesn't stay still. It gets dragged along, pulled in the direction of motion, creating a flow that radiates outward from the moving object before gradually fading back into stillness. The stick doesn't ask the water's permission. It doesn't negotiate. It simply moves, and the medium around it has no choice but to follow at least partially, at least close to the surface. Now replace the water with space-time itself. Replace the stick with a rotating mass. The dragging effect is not a metaphor. It is a real, measurable, physical phenomenon predicted by Einstein's general theory of relativity in 1915, formalized mathematically by Josef Lense and Hans Thirring in 1918, and ignored for the better part of a century because nobody had an instrument precise enough to detect it. The effect is called frame dragging, or the Lense-Thirring effect. The prediction is this: any rotating massive object, a planet, a star, a black hole, twists the space-time around it in the direction of its rotation. Space itself, the geometric fabric through which everything moves, gets pulled along like water behind a moving stick. For Earth, the effect is extraordinarily small. The planet is not particularly massive by cosmic standards, and it rotates at a modest rate. Detecting frame dragging from Earth's rotation requires measuring a change in orientation of approximately 37 milliarcseconds per year, 37 thousandths of 1 arcsecond per year. An arcsecond is 1/3600th of a degree. 37 milliarcseconds is a quantity so vanishingly small that for decades, no gyroscope ever built could measure it. NASA's Gravity Probe, B mission, launched in April 2004 and operating until 2010, was designed to do exactly this. The spacecraft carried 4 gyroscope's spheres of fused quartz, polished to within 40 atoms of perfect roundness, coated with a layer of niobium, cooled to near absolute zero, and spinning in a vacuum so perfect it was considered the best vacuum ever achieved in space. The gyroscopes were oriented at a precise angle relative to a distant guide star. If frame dragging was real, Earth's rotation would cause those gyroscope axes to precess to drift at a predictable rate. The 2011 results confirmed it. The geodetic effect, the warping of space-time by Earth's mass alone, matched the prediction to better than 0.28%. The frame dragging effect matched to within about 19%, consistent with the measurement uncertainties of the extremely small signal. Space-time around Earth is twisting, slowly, almost imperceptibly, but twisting. The water analogy is not poetic. It is literal. Now scale up from Earth to a black hole, and everything changes. For a rotating black hole, what physicists call a Kerr black hole. After Roy Kerr, who derived its mathematical description in 1963, frame dragging is not a subtle effect measured in milliarcseconds. It dominates the entire region of space surrounding the object. Close to a rapidly spinning black hole, there exists a region called the ergosphere, a zone outside the event horizon where space-time is being dragged so violently in the direction of the black hole's rotation that nothing, not matter, not light, not any signal of any kind, can remain stationary relative to the distant universe. Everything inside the ergosphere is forced to co-rotate with the black hole, whether it intends to or not. Think about what that means physically. Imagine trying to stand still in a river. If the current is gentle, you can hold your position by swimming against it. If the current becomes stronger, you must swim harder to stay put. Now imagine a current so powerful that swimming against it at any speed is impossible, even swimming at the speed of light, directed precisely against the flow, cannot keep you stationary. That is the ergosphere. The fabric of space-time is moving faster than anything can move through it. Inside the ergosphere, the black hole's rotational energy becomes accessible from the outside. This is the basis of the Penrose process. Proposed by Roger Penrose in 1971, an object entering the ergosphere can, under the right conditions, split into two pieces, one piece falling into the black hole with negative energy relative to the external universe, and one piece escaping with more energy than the original object possessed. The difference comes from the rotational kinetic energy of the black hole itself, which decreases slightly each time the process occurs. The black hole gives up some of its spin to power the ejected object. Angular momentum, extracted from the black hole's rotation, converted into kinetic energy of escaping matter, accelerated outward. This is thought to be the engine behind one of the most dramatic phenomena in the observable universe, relativistic jets. In April 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole's shadow, the supermassive black hole at the center of the galaxy Messier 87, designated M87*, located approximately 55 million light-years from Earth. The image showed a bright ring of glowing gas with a dark central region, the shadow cast by the event horizon, against the luminous accretion disk surrounding it. In 2023, the collaboration published refined imaging that revealed, with greater clarity than ever before, the base of the relativistic jet emerging from M87*. That jet extends approximately 5,000 light-years into space, 5,000 years of light travel distance, traced in plasma moving at up to 99.9% of the speed of light, powered by the angular momentum of a black hole with a mass 6.5 billion times greater than the Sun. 6.5 billion solar masses. Spinning. Using that spin to fling matter across 5,000 light-years of intergalactic space at nearly the cosmic speed limit. The jet did not begin 5,000 light-years away. It began at the ergosphere of M87*, where frame dragging is not a milli-arcsecond effect, but the fundamental organizing principle of space-time. The rotational energy of the black hole threads through its magnetic field, accelerates plasma, and launches it outward at velocities that would take the particles, if particles can be said to experience anything across 5,000 light-years of the cosmos. The bullet has been in flight for billions of years. It is still flying. M87* does not ask space-time whether it would like to be twisted. It does not consult the surrounding matter about preferred directions. Frame dragging is not an invitation, it is a mandate. When a black hole of 6.5 billion solar masses rotates, the space-time within the ergosphere rotates with it, because the geometry of reality in that region simply has no other option. This is the most literal possible meaning of irresistible attraction, and unlike the metaphorical kind, there is no polite way to decline. Step back for a moment and consider the arc of what rotation has accomplished at this scale. A quantum fluctuation smaller than an atomic nucleus, stretched by cosmic inflation, became a density variation. A density variation became a rotating gas cloud. A rotating gas cloud became a galaxy with a supermassive black hole at its center. That black hole, spinning with angular momentum accumulated across billions of years of accretion, drags space-time around it and flings matter across distances that dwarf the entire solar system by a factor of millions. The same conservation law, the same geometry, the same mathematical inevitability that makes a figure skater spin faster when she pulls her arms in, just scaled to a mass of 6.5 billion suns, operating on the fabric of space itself. From galaxy-scale jets down to light bent around event horizons, rotation permeates the macroscopic universe. But it goes deeper than you think, all the way down to the smallest particles of matter. Rotation, as everyone understands it, is physical motion. A gyroscope spinning on a table, a wheel turning on an axle, Earth rotating on its axis once every 23 hours, 56 minutes, and 4 seconds. In every case, the concept is the same: a physical object moving in a circular path around a defined axis. Something is going around something else, or around itself. Rotation equals motion. The definition feels unassailable. Then you encounter the electron, and the definition collapses. Electrons possess what physicists call spin and intrinsic angular momentum, a property that behaves mathematically like rotation and contributes to the electron's total angular momentum in the same way that physical spinning would. In magnetic fields, electrons behave as though they are tiny spinning magnets, their magnetic moment arising from this spin property. The term itself, spin, invites the mental image of a tiny charged sphere rotating on its axis, generating a magnetic field through that rotation, just as a spinning charged ball would in classical physics. The problem: an electron cannot be spinning in that sense. Not even close. If you take the observed magnetic moment of an electron measured experimentally to extraordinary precision and ask what rotation rate of a classical charged sphere would produce that magnetic moment, you get a surface velocity several hundred times greater than the speed of light, not slightly exceeding it, hundreds of times faster. A physical sphere spinning fast enough to generate the electron's observed magnetic properties would violate the speed of light so catastrophically that the entire framework of relativity would need to be discarded along with it. The electron is not spinning. Its surface is not moving. It is not a tiny sphere of any kind, as far as experiments can determine. Electrons are point particles with no measurable spatial extent whatsoever. And yet spin is real, measurable, and consequential. It interacts with magnetic fields. It determines how electrons pair up in atoms. It is one of the most experimentally confirmed properties in all of physics. So, what is it? Spin is a purely quantum property, what physicists mean when they say something has no classical analog. It is not motion. It is not a process occurring in space. It is an intrinsic state of the particle, as fundamental and irreducible as its mass or charge, characterized by a quantum number. For electrons, that spin quantum number is 1/2. The best analogy available, and it is acknowledged to be imperfect, is a coin. Before you look, a flipped coin is not heads or tails. It is in a superposition, a quantum mixture of both possibilities simultaneously. The moment you observe it, the superposition collapses to one outcome. An electron's spin is similar before measurement. It exists in a superposition of spin-up and spin-down states. The instant a measurement is made, when a magnetic field or a detector interacts with the electron, the superposition collapses, and the electron resolves into one definite spin state. Not because it was secretly in that state all along, and you just didn't know. Because the act of measurement forces the resolution. The spin quantum number of 1/2 carries a mathematical consequence that has no counterpart anywhere in ordinary experience. For a macroscopic object, a ball, a top, a planet rotating 360 degrees around an axis returns the object to its original state. One full rotation equals one full cycle. For an electron, this is not true. Rotating an electron's quantum state through 360 degrees does not return it to its original state. It returns it to the negative of its original state. You need to rotate it through 720 degrees, 2 full rotations, to get back to where you started. This is not a quirk of measurement. It is a deep mathematical property of particles with spin 1/2, arising from the mathematics of spinor representations of rotation symmetry. There is no intuitive picture for it in three-dimensional space, because it does not correspond to anything that exists in three-dimensional space. It is a property of a higher mathematical structure that human intuition was not built to visualize. The first experimental evidence for quantum spin came in 1922, 3 years before the theoretical framework for it was even developed. Otto Stern and Walter Gerlach fired a beam of silver atoms through an inhomogeneous magnetic field, a field that varied in strength across its width. Classical physics predicted that the atoms, which have a magnetic moment due to their electrons, should deflect by varying amounts depending on the random orientations of their magnetic axes, producing a continuous smear on a detector plate. What appeared instead two distinct bands, not a smear, two separate lines, sharply defined. The silver atoms split into exactly two groups, those deflecting fully in one direction and those deflecting fully in the opposite direction. No intermediate values, nothing in between. This was the first direct demonstration that electron spin is quantized, that it takes only discrete values, not a continuous range, spin up or spin down, nothing else. The experiment confirmed that quantum angular momentum does not behave like classical angular momentum in any way that our macroscopic intuitions would predict. You might reasonably be asking, if spin isn't physical rotation, why call it spin at all? Because physicists in 1925 named it before they understood it. Ralph Kronig proposed the concept in early 1925. George Uhlenbeck and Samuel Goudsmit published it independently later that year. They called it spin because it behaved mathematically like angular momentum and produced magnetic effects consistent with something rotating. They didn't know what it actually was. They needed a name. Spin was intuitive. Spin stuck. By the time the theoretical community fully grasped that electron spin had no classical physical interpretation, that it was irreducibly quantum, with no picture available in three-dimensional space, the term was already embedded in every textbook, every paper, every classroom. Changing it would have required renaming half of physics. So quantum spin is a property named by people who didn't know what it was, taught by people who can't fully explain what it is, and used with perfect precision by people who don't need to explain it to calculate with it correctly. That is, arguably, the defining condition of theoretical physics. The name is wrong. The math is exact. The universe doesn't care about the name. Quantum spin is not physical motion, but its consequences determine the entire chemical structure of the universe. Two people cannot occupy the same chair. Two cars cannot park in the same space. You learned this before you learned to read the rule that objects cannot overlap, cannot share position, cannot coexist in the same location at the same time. It feels like common sense. It feels like geometry. It feels, most of all, like it has an obvious explanation. There simply isn't room. The universe has its own version of this rule. It applies to electrons, and it has nothing to do with room. No two electrons in the same system can occupy the same quantum state simultaneously. Not because the space is full, not because electrons repel each other electrically, though they do, but because quantum mechanics categorically forbids it, a prohibition so absolute, so structurally embedded in the mathematics of the universe, that no force, no energy, no physical process has ever been observed to override it. This is the Pauli exclusion principle, formulated by Wolfgang Pauli in 1925. And it is the reason matter behaves the way it does at every scale you have ever encountered. Quantum state here means the complete description of an electron's condition, its energy level, its orbital shape, its magnetic orientation, and crucially, its spin. Two electrons can share the same energy level, the same orbital, the same magnetic quantum number, if and only if their spins are opposite. One spin up, one spin down. That exhausts the available combinations. The third electron has nowhere to go that isn't already occupied. It must move to a higher energy level. The structure of atoms, the layered arrangement of electrons that determines every chemical property of every element, exists entirely because of this constraint. Remove the Pauli exclusion principle and watch everything unravel. Without it, every electron in every atom would cascade down to the lowest available energy state. Hydrogen, helium, carbon, iron, uranium, every element would have all its electrons packed into the ground state orbital, the minimum energy configuration. Every atom in the periodic table would have the same electron structure, different mass at the nucleus, identical electron arrangement everywhere else. What follows from that is not a slightly different chemistry. It is no chemistry at all. Chemical bonding, the process by which atoms link together to form molecules, depends entirely on the specific electron configurations of different elements. Carbon bonds the way it does because it has 6 electrons distributed across 2 shells in a precise arrangement that leaves 4 electrons available for sharing. That arrangement exists because the Pauli principle forced electrons 2 through 6 into specific, differentiated positions, rather than allowing them all to pile into the same state. Without that differentiation, carbon has no reason to form 4 bonds. The entire architecture of organic chemistry, every amino acid, every protein, every strand of DNA, every cell membrane that has ever existed, collapses into a universe where all atoms are chemically identical and therefore chemically inert relative to each other. No covalent bonds, no molecules, no DNA, no life, not life as we don't recognize it, no life of any kind. By any definition, the periodic table is not organized by atomic mass, though mass increases roughly with position. It is organized by electron shell structure, by the way electrons fill available quantum states subject to the Pauli constraint. Each row of the table corresponds to a new electron shell opening up. Each column corresponds to a similar outer electron configuration across different elements. The table's entire architecture is a map of the Pauli principle operating across successive elements. Take away the principle, and the table collapses into a single column, one entry, repeated with increasing mass, but no chemical distinction. Now go in the opposite direction, not atoms, but stars. When a star between roughly 0.8 and 8 times the mass of the Sun exhausts its nuclear fuel, the outward radiation pressure that had been holding it up against gravity disappears. The core collapses, but in most cases, it does not collapse all the way to a neutron star or a black hole. It stops. It becomes a white dwarf, an Earth-sized remnant of compressed stellar material, slowly cooling over billions of years, held up against further gravitational collapse by nothing more exotic than electron degeneracy pressure. Electron degeneracy pressure is the Pauli exclusion principle operating at stellar scales. Compress electrons tightly enough and they begin to resist, not because they repel each other electrically, but because quantum mechanics will not permit them to occupy the same state. Pack them closer together, and their momentum states must diverge to remain distinct. That divergence generates pressure. The pressure holds the star up. The Sun will eventually become a white dwarf. The Pauli principle will keep it from collapsing further. A rule about quantum states derived from the mathematics of spin, supporting an entire stellar remnant against gravitational collapse across timescales measured in trillions of years. For neutron stars denser by a factor of roughly 100 million compared to white dwarfs, the electrons have been crushed out of existence, absorbed into protons to form neutrons. The Pauli principle now operates on neutrons instead. Neutron degeneracy pressure provides the structural support against further collapse. It holds up to a point, the Tolman-Oppenheimer-Volkoff limit, approximately 2 to 3 times the mass of the Sun, depending on the equation of state of dense nuclear matter, marks where neutron degeneracy pressure finally fails. Above that threshold, gravity wins. The neutron star collapses into a black hole. The Pauli principle, which had held it up against gravity across the entire mass range from a fraction of a solar mass to roughly 2 to 3 solar masses, simply runs out of capacity, not because the principle breaks, it never breaks, but because the gravitational energy density finally exceeds what any quantum mechanical pressure can oppose. The hand in front of you right now, the one you might be looking at while reading, is not passing through the surface you're resting it on because of the Pauli exclusion principle. The electrons in your hand and the electrons in whatever surface they're touching are refusing, at the quantum level, to share spin states. That refusal generates an electromagnetic repulsion between the electron clouds that we experience macroscopically as solidity, as texture, as the resistance of matter against matter. You have never actually touched anything in your life. You have only ever experienced the electromagnetic consequence of electrons declining to share quantum states. Handshakes, to be precise about it, are two clouds of electrons arguing about the Pauli principle. The warmth you feel is energy dissipating from that argument. The pressure you feel is the argument failing to resolve. You interpret it as contact. Quantum mechanics describes it as a negotiation between spin states, one that neither party is willing to concede. The implications extend beyond chemistry and stellar physics into the deepest question the Pauli principle raises. Why does spin create this exclusion at all? The answer connects to a branch of mathematics called the spin statistics theorem, a result showing that particles with half-integer spin, called fermions, must obey the Pauli exclusion principle, while particles with integer spin, called bosons, do not. Photons are bosons. Any number of photons can occupy the same quantum state simultaneously. This is what makes lasers possible. Coherent light with enormous numbers of photons in identical states. Electrons are fermions. No two can share a state. The distinction traces directly back to how different types of particles transform under rotational symmetry in quantum field theory. The mathematics of rotation, applied at the deepest level of particle physics, determines whether matter can stack or whether it must differentiate. Spin, in other words, is not just a property of individual particles. It is the organizing principle of matter itself. It decides which particles are the building blocks subject to the exclusion that forces structural diversity, and which particles are the messengers, free to pile up without limit. Remove spin, and the distinction vanishes. Remove the distinction, and the universe has no mechanism for building complex structures from simple components. Quantum spin built the periodic table. It built the molecules that built you. It is holding the surface beneath you up against your weight right now, and has been doing so without interruption since before the Earth formed. Quantum spin builds chemistry. But why does spin exist at all? Why does the universe have rotational symmetry in the first place? That question is not physics. It is pure mathematics. Conservation laws feel like rules. Not arbitrary rules, not rules someone made up in a committee meeting, but rules in the sense that speed limits are rules. They exist. They apply. They have consequences when violated, and most people simply accept them without asking where they came from. Energy is conserved. Momentum is conserved. Angular momentum is conserved. These are the load-bearing walls of physics, the constraints that every process in the universe must respect. Students learn them early. Physicists use them constantly. Almost nobody asks the deeper question, why do these laws exist at all? What compels the universe to conserve anything? The answer is not in any physics equation. It predates the physics. It lives in pure mathematics. And it was proved in 1915 by a woman who was not officially allowed to hold an academic position at the institution where she was doing the work. Emmy Noether's theorem states every continuous symmetry of a physical system corresponds to exactly one conserved quantity. One-to-one correspondence. No exceptions. No fine print. The relationship is not approximate, not empirical. not inferred from experiment. It is mathematically proven, a logical consequence of how symmetry and dynamics interact in any system describable by a principle of least action, which includes every physical theory we have ever successfully built. Symmetry, in the mathematical sense, means invariance under transformation. Something is symmetric if you can do something to it, and it looks identical afterward. A circle has rotational symmetry, rotate it by any angle around its center, and you cannot tell it moved. A square has discrete rotational symmetry, rotate it by 90 degrees, and it looks the same, but rotate it by 45 degrees, and the difference is visible. Noether's theorem applies specifically to continuous symmetries, those that can be applied in infinitely small increments, like rotation by any arbitrary angle, not just by fixed steps. Work through the three most consequential examples carefully, because each one connects something you might never have imagined to be related. Time symmetry. The laws of physics are the same today as they were yesterday, as they were 1 billion years ago, as they will be 1 billion years from now. Run an experiment in your laboratory on a Tuesday. Run the identical experiment the following Thursday. The results are the same. The rules have not drifted. This invariance, the fact that shifting the moment at which you observe physics does not change the physics, is a continuous symmetry. Noether's theorem connects it directly and inevitably to conservation of energy. Energy is conserved not because the universe decided to conserve it, but because the laws of physics do not change over time. If they did, if the rules shifted moment to moment, like stock prices, energy would not be conserved. The two facts are the same fact, viewed from different angles. Translational symmetry. Move your laboratory from Paris to Tokyo, to a space station orbiting Jupiter. The laws of physics work identically in all three locations. No spatial position in the universe is privileged. Changing where you are does not change the rules. That invariance continuous symmetry under spatial translation connects directly to conservation of linear momentum. Momentum is conserved because space is uniform. Same theorem, same logic. Rotational symmetry. Turn your laboratory to face north, then east, then toward a random point between two stars. The laws of physics remain identical regardless of orientation. No direction in space is special. This invariance continuous symmetry under rotation connects directly to conservation of angular momentum. Angular momentum is conserved because the universe has no preferred direction, not because someone decided angular momentum should be conserved. Because the geometry of space makes no distinction between one direction and any other. To feel why this matters, construct the alternative. Imagine a universe with a special direction, call it cosmic north. In this hypothetical, the laws of physics behave slightly differently, depending on whether your experiment points toward cosmic north or away from it. Rotational symmetry is broken. Noether's theorem immediately implies that angular momentum is no longer conserved. Spinning objects in this universe could spontaneously slow down or speed up as they rotate through different orientations relative to cosmic north. No stable orbits would be possible. The angular momentum, maintaining every planetary trajectory, would bleed away unpredictably. Galaxies could not hold their disk structure. The entire large-scale architecture of the cosmos, built on the assumption that angular momentum accumulated 4 billion years ago, is still present and preserved today, becomes impossible. Think of it in terms of a card game. Suppose you are playing poker, and the rule for what hand beats what depends on which direction you are facing at the table. A flush beats a full house when you face east, but not when you face west. That is a game without rotational symmetry. The rules change with orientation. In our universe, physics is not that game. The rules are identical regardless of which way you are facing. That equivalence, trivial as it sounds when stated plainly, is the entire foundation of angular momentum conservation. The sameness of physics across directions locks every unit of angular momentum in place. Einstein described Noether's theorem as the most significant piece of creative mathematical thinking since the emergence of higher mathematics. That is not the praise of a colleague being polite. Einstein understood, as well as anyone ever has, what it means to connect geometry to physics. His own general theory of relativity is built on the relationship between the curvature of spacetime and the distribution of energy and momentum. But Noether found something more fundamental, a bridge between the symmetry structure of space itself and the conservation laws that govern every physical process within it. The theorem does not describe the universe's behavior. It explains why the universe must behave that way. The consequences spiral outward across every scale considered in this series. The quantum fluctuations in the early universe that seeded all structure, they generated angular momentum, precisely because the universe had no preferred direction to absorb it into. The collapse of the solar nebula, 4.6 billion years ago, conserved every unit of angular momentum across the compression because rotational symmetry guaranteed it. The neutron star, spinning 716 times per second, carries angular momentum that originated in a stellar core millions of times larger, and not one unit has been lost in the collapse. Because nothing in the universe has the authority to violate the symmetry that demands its conservation. The frame-dragging effect of a rotating black hole, twisting spacetime across thousands of light years. The angular momentum driving it has been accumulating since the black hole's parent material first began to rotate. And it has been accumulating without loss. Same theorem, same symmetry, same conservation. From quantum fluctuations smaller than an atomic nucleus to black holes 6.5 billion times the mass of the Sun, one mathematical result connects them all. Noether herself was refused a faculty position at the University of Göttingen in 1915. The same year she proved the theorem. The Senate reportedly objected on the grounds that women should not be permitted to teach at the university. David Hilbert, one of the greatest mathematicians who ever lived, reportedly responded that he could see no reason why the candidate's gender should be relevant to the quality of her mathematics, and pointed out with characteristic precision that the institution was not a bathhouse. He allowed her to lecture under his own name until her position was eventually formalized. Her work circulated. Her credit, for years, did not. The universe has never noticed the distinction. It has been running on her theorem for 13.8 billion years, conserving angular momentum with a precision of 1 part in 100 trillion, without any record of her having been refused employment. The cosmos has no human resources department, no credentialing hierarchy, no mechanism for deciding whose mathematics counts. It simply follows the logic. It has no other option. Rotational symmetry preserves angular momentum, and that angular momentum, conserved without interruption across 13.8 billion years, is right now deciding whether you can survive on the planet beneath you. Every compass needle that has ever pointed north, every migratory bird that has ever crossed an ocean and arrived at the correct continent, every satellite navigation system that accounts for magnetic declination. All of it depends on a field that most people accept as a background feature of the planet present, reliable, unremarkable. Earth has a magnetic field? Of course it does. It always has. Most people file this away and never ask where it comes from, how it stays on, or what would happen if it didn't. The answers to those questions are considerably more disturbing than the question itself suggests. Earth's magnetic field is not produced by a giant permanent magnet buried in the interior. There is no magnetized iron bar at the core generating field lines the way a refrigerator magnet generates its modest pull. Permanent magnets lose their magnetization above a temperature called the Curie point for iron, roughly 770 degrees Celsius. Earth's core sits at temperatures between 4,000 and 6,000 degrees Celsius. No permanent magnet survives those conditions. Whatever is generating Earth's magnetic field, it is not a static structure. What it actually is, a dynamo, a self-sustaining electromagnetic generator running continuously inside the planet, powered at its foundation by Earth's rotation. The outer core of Earth, sitting between roughly 2,900 kilometers and 5,150 kilometers below the surface, is composed primarily of liquid iron and nickel. Both metals conduct electricity. The outer core is not static. It convects, driven by heat flowing outward from the inner core and by the release of latent heat as the inner core slowly solidifies over geological time. Hot material rises, cool material sinks, and the result is a churning ocean of conductive liquid metal several thousand kilometers deep. Convection alone does not produce a dynamo. What organizes the convective flows into the structured, large-scale circulation patterns needed to sustain a magnetic field is the Coriolis force, a direct consequence of Earth's rotation. The Coriolis force acts on any fluid moving across a rotating body. It deflects motion to the right in the northern hemisphere, to the left in the southern, and at the scale of Earth's liquid outer core. It organizes the convective columns into coherent helical structures aligned roughly parallel to the rotation axis. Those organized helical flows of conductive liquid metal, moving through an existing magnetic field, generate electric currents. Electric currents generate magnetic fields. Those magnetic fields drive more currents. The system is self-reinforcing, a feedback loop that has been running without interruption for at least 3.5 billion years, and possibly longer. The analogy to a power station generator is exact in its physics, if not in its scale. In a generator, copper wire coils rotate through a magnetic field, and the motion of conductive material through the field induces current. On Earth, liquid iron columns rotate through the existing field due to Coriolis organized convection, and the motion induces current. The principle is identical. The scale is the interior of a planet. What breaks the dynamo is straightforward: remove the rotation, and the Coriolis force vanishes. Without Coriolis organization, the convective flows become turbulent and unstructured random churning rather than coherent helical columns. The large-scale circulation patterns that sustain the current loops collapse. The dynamo dies. The field fades. And without the magnetic field, what follows is not an inconvenience. It is a slow catastrophe. Mars shows exactly what that catastrophe looks like, played out over geological time. Mars had a magnetic field. The evidence is preserved in the magnetized ancient crust of the southern highlands regions of rock that locked in the orientation of a global magnetic field when they solidified more than 4 billion years ago. Just as lava on Earth preserves the magnetic field direction at the time of its cooling. Roughly 4 billion years ago, something ended the Martian dynamo. The leading explanation is that Mars, being smaller than Earth, cooled faster. Its core lost enough heat that the temperature difference driving convection dropped below the threshold needed to sustain organized flow. The dynamo stopped. The global magnetic field disappeared. What followed took a few 100 million years, but it was irreversible. Without a magnetic field to deflect the solar wind, the continuous stream of charged particles flowing outward from the sun at speeds between 300 and 800 kilometers per second, the Martian atmosphere was exposed. Solar wind particles, undeflected, struck the upper atmosphere directly, transferring energy to atmospheric molecules and gradually accelerating them to escape velocity. The process is called atmospheric sputtering and ion escape, and it works slowly but relentlessly. NASA's MAVEN mission, the Mars Atmosphere and Volatile Evolution spacecraft, operating on data collected from 2015 onward, measured the current rate of atmospheric loss from Mars directly. The solar wind is still stripping the Martian atmosphere at a rate of approximately 100 grams per second. Every second, continuously. 4 billion years of this process has reduced the Martian atmosphere to a thin remnant. Current surface pressure on Mars is approximately 0.6% of Earth's sea level pressure. Standing on the Martian surface without a pressure suit, your blood would boil? Not from heat, from the near total absence of atmospheric pressure. The liquid water that once flowed across Mars, carving the valley networks visible today, cannot exist as liquid on the surface anymore. The conditions for it evaporated along with the atmosphere over the geological timescale following the death of the dynamo. Earth's atmosphere exists right now, above you, holding the pressure that keeps your blood liquid and blocking the X-ray and ultraviolet radiation that would otherwise reach the surface because Earth is rotating. The rotation drives the Coriolis force. The Coriolis force organizes the outer core convection. The convection sustains the dynamo. The dynamo maintains the magnetic field. The magnetic field deflects the solar wind. The solar wind, deflected, cannot strip the atmosphere. The atmosphere remains. You breathe. That chain has no redundant links. Break any one of them, and you end up with Mars. We have spent decades and enormous amounts of institutional energy worrying about climate change, nuclear weapons, asteroid impacts, pandemic pathogens, all legitimate concerns, all genuinely dangerous. But the thing actually keeping the surface of this planet habitable, the mechanism without which the atmosphere would have been gone billions of years ago, is a self-sustaining liquid iron engine spinning at 2,900 kilometers depth, organized by the Coriolis effect of a planetary rotation that has been slowing by 1.7 milliseconds per century since the Moon began stealing angular momentum from it. Nobody worries about the geodynamo until they look at Mars. Mars is the worry made geological. The magnetic field protects the atmosphere, but rotation does something else entirely. Something that determined not just whether life could survive on Earth, but what kind of life, across what timescales, with what seasonal rhythms and climatic stability. Spring, summer, autumn, winter. 4 seasons. Cycling annually. Shaping agriculture and ecology and the entire rhythm of life at temperate latitudes. Everyone learns the cause in school. Earth's rotation axis is tilted 23.5 degrees relative to the plane of its orbit around the Sun. When the northern hemisphere tilts toward the Sun, it receives more direct sunlight across more hours of the day summer. When it tilts away, sunlight arrives at a shallower angle across fewer hours winter. The explanation is clean. The diagram is simple, and most people's curiosity stops there. Nobody asks the follow-up questions. And the follow-up questions are where the story actually lives. What if the tilt were 0? No axial tilt at all. Earth's rotation axis pointing straight up, perpendicular to the orbital plane. The immediate consequence is the obvious one: no seasons. Each latitude receives the same amount of sunlight year-round. Stable, predictable, uniform. Sounds reasonable. Perhaps even appealing? But work through the implications. With no seasonal variation redistributing heat, the poles receive consistently low-angle sunlight every day of the year, and they freeze. Permanently, deeply, without interruption. The polar ice sheets grow without the summer melting that currently limits them. The tropics receive consistently intense solar radiation 12 months per year, generating heat that the altered atmospheric circulation patterns distribute differently than they do now. The climate stabilizes, but into a configuration far more extreme at the latitudinal margins. Permanently glaciated poles, permanently scorched tropics, and a narrow habitable band in between, not hospitable to the complex. High-latitude ecosystems that currently cover much of North America, Europe, and Asia. Now push in the other direction. Uranus has an axial tilt of 97.77 degrees, essentially rolling on its side as it orbits the Sun. the consequences are severe. During Uranian summer, the pole pointing toward the sun receives continuous sunlight for roughly 42 Earth years. During winter, that same pole sits in continuous darkness for 42 years. The other pole simultaneously experiences the opposite. The temperature swings are extreme. The seasonal timescales are measured in decades rather than months, and no biological process built around annual cycles has any foothold. Complex life requires rhythm. Rhythm requires predictability. Predictability requires a tilt that changes the seasons on timescales short enough for organisms to adapt and long enough for ecosystems to stabilize. 97.77 degrees provides neither. 23.5 degrees is not an obvious optimum. It is not the result of any optimization process. It is, on the face of it, a number that could have been anything a cosmic accident, like the precise speed of Earth's orbit or the exact mass of Jupiter. Except it is not quite an accident. It is the outcome of a specific collision, and it is stabilized by a specific gravitational relationship that has been running for 4.5 billion years. Without the Moon, Earth's axial tilt would not stay at 23.5 degrees. It would not stay anywhere. Jacques Lascar and colleagues, in a 1993 study that has since become a landmark in planetary science, calculated what Earth's axial tilt dynamics would look like in the absence of the Moon. The answer: chaotic oscillation between approximately 0 and 85 degrees on timescales of millions of years, not gradual drift. Chaotic, large amplitude wandering the tilt could swing from nearly upright to nearly horizontal and back over geologically short intervals, driven by gravitational resonances with the other planets that the Moon's angular momentum currently prevents from taking hold. The Moon stabilizes Earth's axial tilt by contributing angular momentum to the Earth-Moon system in a configuration that damps those resonances. The Moon's gravitational torque on Earth's equatorial bulge acts as a gyroscopic stabilizer, resisting the perturbations that would otherwise send the tilt careening. Without that stabilization, climate on Earth would swing between the zero tilt extreme and the near horizontal extreme on million-year cycles, making stable, long-duration ecosystems effectively impossible. Evolution requires time, not just millions of years, hundreds of millions of consistent years. With climate remaining within bounds that permit complex chemistry, liquid water, and the seasonal rhythms that biological systems have organized themselves around. Chaotic axial oscillation eliminates that consistency. Where did the Moon come from? From a collision? Approximately 4.5 billion years ago, a Mars-sized body, designated Theia in the scientific literature, struck the early Earth at an oblique angle. The impact was not head-on, it was off-center, a glancing blow that injected an enormous quantity of angular momentum into the Earth-Moon system. Debris from the collision, carrying that angular momentum, assembled in orbit around Earth and coalesced into the Moon over thousands of years. The Moon began its existence much closer to Earth, perhaps 15 to 20 Earth radii away, compared to its current 60 Earth radii, and has been receding ever since. As the tidal braking mechanism described earlier continues to transfer angular momentum from Earth's rotation outward into the Moon's orbit, the angular momentum of the Theia impact did not just create the Moon. It set the initial conditions for the axial stabilization that made complex life possible. The off-center geometry of the collision determined how much angular momentum entered the system. That angular momentum became the Moon's orbital motion. That orbital motion provides the gravitational torque that stabilizes Earth's tilt. The tilt stability enables consistent seasons. The seasons enable the agricultural cycles that underpin every human civilization. A 2023 study by Quarles and Lissauer, published in the Astronomical Journal, modeled the axial tilt stability of Earth-like planets across a range of conditions with and without large moons, at various orbital configurations. Their conclusion reinforced what Lasker's earlier work implied: the combination of Earth's rotation, the Moon's angular momentum, and the resulting axial tilt stability is an unusual configuration, not impossible to replicate elsewhere, but not common. Many planets around Sun-like stars will lack a large stabilizing moon. Many will have axial tilts that wander chaotically. The fraction that maintain the stable, moderate tilt needed for complex life across the hundreds of millions of years that evolution requires is genuinely small. This may be part of the answer to the Fermi paradox, the question of why. In a universe containing hundreds of billions of galaxies, each containing hundreds of billions of stars, with planetary systems now known to be common, we have detected no evidence of other technological civilizations. The universe is full of planets. Planets with stable axial tilts, sustained by the angular momentum of a large moon that formed from an off-center collision at exactly the right time in the planet's early history, sitting in the habitable zone of a stable star, with a geodynamo generating a protective magnetic field. That combination is rarer, perhaps substantially rarer. The angular momentum conditions that made Earth habitable are not guaranteed. They are a particular outcome of particular initial conditions, and those conditions do not replicate themselves everywhere. Theia struck 4.5 billion years ago. The impact lasted perhaps an hour. The angular momentum it deposited into the Earth-Moon system has been doing work ever since, stabilizing the tilt, enabling the seasons, underwriting the long-term climatic consistency that allowed single-celled life to become multicellular life, to become vertebrates, to become the species currently reading this sentence. Shakespeare wrote, because Theia hit at the right angle. Einstein derived relativity because the collision preserved enough angular momentum to keep a large moon in orbit. The entire corpus of human art, science, philosophy, and inquiry exists downstream of an impact that the universe did not plan, did not intend, and could not have predicted. The universe was not trying to produce you. It was just following the physics. And yet, from quantum fluctuations smaller than an atom, to you sitting here breathing, thinking, all of it is connected by one invisible thread rotation. The question is not why everything spins. The question is, what happens when we truly understand why? From a quantum fluctuation smaller than an atomic nucleus to a relativistic jet stretching 5,000 light years, the same law, the same symmetry, the same conservation, unbroken across 13.8 billion years. Every scale in this series, from the electron's intrinsic spin to the ergosphere of a black hole 6.5 billion times the mass of the Sun, obeys identical mathematics, not similar principles, the same equation, the same geometry, the same accounting. Rotation is not something the universe does. It is what the universe is. Strip away the galaxies, the stars, the atoms. What remains at the foundation is symmetry. Rotational symmetry, no direction special, no orientation privileged. That single geometric fact, through Noether's theorem, produces conservation of angular momentum. Conservation of angular momentum produces everything else. The spinning is not incidental. It is the signature of the universe's deepest structure, written at every scale simultaneously. But Noether's theorem only tells us that rotational symmetry produces conservation. It does not tell us why the universe has that symmetry in the first place. Why is space isotropic? Why no preferred direction? Modern physics stands at that question and goes quiet, not from lack of effort, but because the tools to ask it correctly may not yet exist. Perhaps rotational symmetry is a necessary property of any universe stable enough to contain structure. Perhaps rotation is simply the only language the universe knows, and 13.8 billion years of spinning matter is the longest sentence ever spoken. Or perhaps the answer lives at a depth of physical reality we haven't reached yet beneath quantum field theory, beneath space-time geometry, at a layer we don't have instruments to see. Standing at the edge of understanding is not a failure. An answer closes a door. An open question holds it wide. The universe is still spinning. It doesn't need an explanation to continue. But somewhere inside it, one small species noticed the spinning, traced it from quantum foam to galactic jets, found the same law threading through all of it, and looked out past the edge of what it knows. That, too, is a consequence of rotation, and it may be the most extraordinary one of all.